Parametric devices by Dr. C.P. Vartani, Department of Physics, Osmania University. Parametric devices uses non-linear reactance or time-varying reactance. Parametric term is derived from parametric excitation, since the capacitance or inductance, which is a reactive parameter, can be used to produce capacitive or inductive excitation. Parametric excitation is subdivided into parametric amplification and oscillation. Many of the essential properties of non-linear energy storage systems were described by Faraday and Lord Rayleigh. The first analysis of non-linear capacitance was given by Van der Zeel in 1948, who suggested that such a device might be useful as a low noise amplifier, since it was essentially a reactive device in which no thermal noise is generated. In 1949, Landon analyzed and presented experimental results of such circuits used as amplifiers, converters, and oscillators. In the age of solid-state electronics, microwave electronics engineers thought of a solid-state microwave device to replace the noisy electron beam amplifier. In 1957, Sohal proposed a microwave solid-state amplifier that used ferrite. The first realization of a microwave parametric amplifier was made by Wess in 1957, after which the parametric amplifier was last discovered. At present, the solid-state varactor diode is the most widely used parametric amplifier. Unlike microwave tubes, transistors, and lasers, the parametric diode is of reactive nature and thus generates a very small amount of Johnson noise called the thermal noise. Parametric amplifier utilizes an AC rather than a DC power supply, as microwave tubes do. In this respect, the parametric amplifier is analogous to the quantum amplifier, laser, or maser, in which an AC power supply is required. A reactance is defined as a circuit element that stores and releases electromagnetic energy as opposed to a resistance which dissipates energy. If the stored energy is predominantly in the electric field, the reactance is said to be capacitive, inductive if the magnetic field. C is equal to Q by C. C is equal to Q by V. If the ratio is not linear, the capacitive reactance is said to be non-linear. In this case, it is convenient to define a non-linear capacitance as the partial derivative of charge with respect to voltage. That is, C of V is equal to dq by dt. The analogous definition of non-linear inductance is L of I is equal to d phi by di. In the operation of parametric devices, the mixing effects occur when voltages at two or more different frequencies are impressed on a non-linear reactance. Parametric amplifier outlines will study the basics of parametric amplifier, circuit of parametric amplifier, working of parametric amplifier, advantages of parametric amplifier, disadvantages and applications of parametric amplifier. Basics of parametric amplifier. It is highly sensitive low noise amplifier. It is used for ultra high frequency and microwave frequency. It utilized active elements like inductor and capacitor. By changing reactance, it amplifies signals using pump circuit. Varactor diode is most commonly used as a variable reactor. This is a circuit of a parametric amplifier, where the input is AC, the frequency of Fg, Rin is input resistance, and band pass filter. This is intermediate frequency. Band pass filter RF frequency, which is inductance in series with the capacitance, and we have a pump circuit with a with the frequency Fp, and RLO is a local oscillator, and VCO is the voltage of the local oscillator, and in band pass filter of the local oscillator is inductance in series with the capacitance, is connected to the output of the RF circuit, and output of this pump circuit is connected to a varactor diode. With a varactor diode, the capacitor varactor diode has got a variable capacitance and a resistor, and band pass filter circuit in series with the band pass filter circuit which is IF, intermediate frequency output. Then F0 is the output frequency, which is measured across the load RL, and F0 is the frequency, output frequency is equal to Fp plus Fg and or Fp minus Fg. Here we have output power is either at Fg plus Fp or Fp minus Fg. As per Manley-Roe equation, we have maximum gain can be given as F0 by Fg is equal to Fp plus Fg by Fg, which is equal to 1 plus Fp by Fg. This is a theoretical gain, but practically it is less than it. And if output frequency is Fp plus Fg, then the parametric amplifier is called up converter and works as amplifier. If output frequency is Fp minus Fg, then the parametric amplifier is called down counter. It doesn't amplify the signal, rather it creates losses. So, what are the advantages of parametric amplifier? Noise figure. Due to less resistance, it is there in range of 1 to 2 decibels. And the frequency range, it covers wide range of frequencies, about 1 GHz to 200 GHz. And the disadvantages, it has got the bandwidth less due to tuned circuit, but it can be increased by stagger tuning. And the gain is limited to 20 to 80 decibels. And applications, low noise amplifier LNE, space communication, and the topo receiver or the radios and radio telescope. This Manley-Roe power relations derived a set of general energy relations regarding power flowing into and out of an ideal non-linear reactance. These relations are useful in predicting whether power gain is possible in a parametric amplifier. This is the equivalent circuit for Manley-Roe derivation. Fs, the source frequency, Fp is the pump frequency, and reactance, capacitor reactance connected in parallel. Then we have Fp plus Fs, Fp minus Fs, and mFp plus mFs. So we have one signal generator and one pump generator at their respective frequencies Fs and Fp together. With associated series resistances, band pass filters are applied to a non-linear capacitance C of t. These resonating circuits of filters are designed to reject power at all the frequencies other than their respective signal frequency. In the presence of two applied frequencies Fs and Fp, an infinite number of resonant frequencies of mFp plus or minus nFp are generated where m and are integers. Each of the resonating circuits is assumed to be ideal. The power lost by the nonlinear susceptance is negligible. That is, the power entering the nonlinear capacitor at the pump frequency is equal to the power leaving the capacitor at the other frequencies through the nonlinear interaction. Manley and Roe established the power relations between the input power at the frequencies Fs and Fp and the output power at the other frequencies mFp plus or minus nFp. It is assumed that the signal voltage Vs is much smaller than the pumping voltage Vp, and the total voltage across the nonlinear capacitance C of t is given by V is equal to Vp plus Vs, and Vp, then this is can be, if it's AC form, this AC is written as Vp by 2 e to the power of j in omega p plus e to the power this exponential of the power frequency, and we have the source frequency. Then the general expression of the charge Q deposited on the capacitor is given by Q is equal to the summation m is minus infinity to plus infinity, n is minus Q of m n e to the power of j m omega pt plus n omega s plus t. So for Q to be ideal, Qmn is equal to Q star minus conjugate or minus m minus n. The total voltage V can be expressed as a function of the charge Q. A similar Taylor series expression V of Q shows that V is equal to such m is minus infinity, n is minus infinity to plus infinity. V of m is the equation. V to be real, V of mn is equal to V star minus m minus n. The current flowing through C of t is the total derivative of Q with respect to time and is given I is equal to dq by dt. This is the final expression and I of mn is calculated. Since the capacitance C of t is assumed to be pure reactance and the average power at the frequencies m f of p plus n f of s is given by so and so, then the conservation of power can be written as summation m is minus infinity to plus and infinity and n is equal to minus p of mn is 0. Multiplying on the above equation by factors so and so will get the result is resulting into two parts yield so and so. So we know, so then we have the IMN and PMN also calculated. It becomes so and so and is independent of omega p or omega s. For any choice of the frequencies f of p and f of s, the resulting circuit external to that of the non-linear capacitance can be adjusted that the currents may keep all the voltage amplitudes p of mn unchanged. So the charges are also unchanged since they are functions of voltages. So consequently, the frequencies f of p and f of s can be arbitrarily adjusted in order to require so and so m p of mn and p of mn which is equal to 0 and equation that can be expressed so and so. Since we know our p value, therefore we get summation of both and where omega p and t plus by fp and fs. The above equations are standard forms for the Manley Rowe power relations. The term P of Mn indicates the real power flowing into or leaving the non-linear capacitance at a frequency of m f of p plus n f of s. The frequency f of p represents the fundamental frequency of the pumping voltage oscillator and the frequency f of s signifies the fundamental frequency of the signal voltage generator of the input. The sign convention for the power term P of Mn will follow the power flowing into the non-linear capacitance or the power coming from the two voltage generators is positive, whereas the power leaving from the non-linear capacitance or the power flowing into the load resistance is negative. So consider for instance the case where the power output flow is allowed at a frequency of f of p plus fs as shown in the figure. Thank you.